In this video, we're going to look at some substrates that make good electrophiles for SN and E reactions. This expands our synthetic ability to make different types of compounds and do different transformations using our SN1, SN2, E1, E2 reactions from chapters 8 and 9. And most of what I'm talking about is featured in chapter 10 in the Karty text. Up until now, our major substrates for reactions both in the Stromanis book and in Karty have been alkyl halides, something with a chlorine, bromine, or iodine, weak base, good leaving groups attached to sp3 carbons. We've also seen in the Stromanis book this mysterious ROTS, ROMS, ROTF as equivalently good leaving groups to the halides. What these actually are is leaving groups that make conjugate bases of the strong acid sulfonic acids, such as the ones shown, where you have your carbon that's doing the reacting attached to an oxygen attached to an S double bond O with an R group. And the identity of the R group determines whether it's a TS for a toluene sulfonyl group, an MS for a methyl sulfonyl group, or a TF for a trifluoromethyl sulfonyl group. The group itself, the leaving group, is this thing right here, which is a resonance stabilized anion, very weak base. Now, alcohols play a central role in organic chemistry, and many alcohols can be made in many ways we have yet to learn about. It would be nice if we could make alcohol, the OH, into a good leaving group. By itself, it is a poor leaving group. The oxygen, if it left with an OH minus, would be a strong base, poor leaving group. But we can make it into a good leaving group in a variety of ways. In chapters 8 and 9, we look at using a mineral acid for this. For example, we can use a hydrohalic acid, where X is iodine, bromine, or chlorine. And the oxygen reaches out to grab onto the H+. The X leaves with its lone pair of electrons, weak base, and we end up with the conjugate acid of the alcohol. This conjugate acid of the alcohol is an excellent leaving group, and when it leaves and takes its lone pair of electrons with it, it becomes water. If this occurs through an SN2 reaction, that is, if the substrate is unhindered, then we would get our inversion product through an SN1 pathway along with our water leaving group. On the other hand, this could also occur through an SN1 pathway, in which we went through a carbocation intermediate with the leaving group of water, and the carbocation intermediate could approach the p orbital from either side in order to form a racemic mixture of alkyl halide products. Again, this would only happen for substrates that would have stable carbocations, such as conjugated, allylic, benzylic, or hindered, such as hindered secondary or tertiary substrates. Likewise, an ether can be made into a good leaving group. OR minus is normally a very poor leaving group, strong base, but if you add an appropriate hydrohalic acid, and in this case only iodic acid and hydrobromic acid are strong enough acids to make this happen, then we create an intermediate that would have a good leaving group. That is, a leaving group that would become an alcohol when it leaves, to give us, when our halide replaces it, an alkyl halide and an alcohol leaving group. And this would happen again via an SN1 or SN2 process depending on the hindrance of the substrate. For anything that has any remote stability of the carbocation, secondary, tertiary, or allylic benzylic, under these strong acid conditions, SN1 would be preferred, and we'd end up with both stereoisomers. But for substrates that are unhindered primary or methyl, this could pass through an SN2 pathway and give you only one enantiomer of your halide. In chapter 10, we're given a new reagent that will also give you an outcome of SN2 only for alkyl halides, and that is your phosphorus trichloride, or phosphorus tribromide. This very cleanly gives you, through SN2 only, the SN2 inversion product, where X equals bromine or chlorine, and a side product which includes the phosphorus with the leaving oxygen and the two halides. This happens by the oxygen acting as a nucleophile towards the electrophilic phosphorus atom, with the subsequent leaving of a chloride to give a mechanistic intermediate that has a positively charged oxygen atom. When this group leaves, taking its electrons with it, it gives us our neutral phosphorus oxygen compound. It gives us a good leaving group and allows us to bring our nucleophile in for SN2 to give us our inversion product. This reaction with either PCl3 or PBr3 is much cleaner than using HX when you can do an SN2 reaction, that is methyl primary or unhindered secondaries, and is the reagent of choice, or replacing an OH group with a chloride or bromide group through SN2. And it is the reagent of choice for replacing an alcohol OH with a halide for unhindered substrates. A second electrophile that's introduced in Chapter 10 is the epoxide ring. The epoxide ring is a three-membered ring, and so it's strained, and the C8CO bonds are rather weak and easy to break. So even though epoxide might have to leave as an O-, particularly under neutral or basic conditions, it will do so readily because it relieves the strain in the three-membered ring. Under acidic conditions, we protonate the oxygen first, making an even better leaving group. So the epoxide ring oxygen in the presence of a mineral acid will protonate first in an acid-base reaction to give a very reactive intermediate. In fact, the intermediate is going to elongate its CO bonds, and particularly the CO bond towards the more substituted center, like so, creating a fairly large delta positive on the more substituted carbon atom as that bond elongates. This would allow a nucleophile to come in and react at that delta positive center, breaking the OC bond and making a bifunctional compound where the OH of the epoxide was the original oxygen, and over here at the more substituted center, our nucleophile has come in from the opposite side, SN2, to make a new bond. So we have a 1,2 disubstituted compound where whatever the nucleophile is breaks that bond. We can form products that are 1,2 difunctionalized with nucleophiles that can exist in the presence of a strong acid, such as the halide ion from HCl or HBr or HI. It will also work with H plus and water to eventually make dihydroxide, or H plus and an alcohol to make an alcohol group on the primary and an ether group on the secondary. On the other hand, if we have a basic nucleophile, such as the cyanide ion, hydroxide ion, or alkoxide ion, we can add those directly to the epoxide without prior protonation. And that's the strain in this three-membered ring that will allow this to work as a good electrophile. There is already somewhat of a delta plus on each of the two carbon atoms. However, neither of the two bonds is particularly elongated. So without the addition of an acid, we would get a normal SN2-like reaction, in which our nucleophile will approach the less hindered center as the CO bond breaks, to give us a bifunctional compound. That is, the nucleophile ends up on the less hindered position. That's the bond that's broken, and the more hindered position retains the oxygen as well as its original stereochemistry. In this case, O- is a leaving group, even though it's a pretty strong base, because in the process we break this very weak carbon-oxygen bond and relieve the strain of the three-membered ring. A second step of this reaction must be the abstraction of a proton from some acidic site, often solvent, that will allow us to get our bifunctional compound in which the nucleophile ends up at the less hindered center and the alcohol at the more hindered center. So again, under acidic conditions, we protonate first, elongate the internal bond to the more substituted carbon, and the nucleophile adds at that center in an inversion SN2 pathway. Under basic conditions, the nucleophile comes into the less hindered pathway since neither of the bonds are particularly elongated, allowing the nucleophile to substitute at the less hindered center, and after protonation we get nucleophile less hindered, alcohol more hindered. In both cases, we make a bifunctional 1,2 compound. And our third and final example of a different electrophile for our reactions is going to be for an E2 reaction called the Hofmann elimination. In the Hofmann elimination, we have an amine, and we add to it an excess of methyl bromide in the presence of sodium hydroxide and heat. Heat right away should be a clue that there's probably elimination taking place. The fact that NaOH is a relatively strong base is a clue that the elimination is going to take place by E2. But before we do that, we have to have a good leaving group, and certainly NH2- is a very poor leaving group. As we'll see in the other synthesis video for this week, when you react nitrogen with an excess of a very good electrophile like methyl bromide, it will continue to alkylate until it runs out of alkyl groups to add. So in fact, the NH2 originally does an SN2 with methyl bromide, loses a proton through acid base, does another SN2 with methyl bromide, loses a proton through acid base, does a third SN2 with methyl bromide, and it has no proton to further lose, and you end up with 3 methyls on the nitrogen atom, the nitrogen with a positive charge, and now we have an excellent leaving group. If that leaving group were to leave and take its electrons with it, it would create a carbocation. But it turns out that because we have a fairly strong base in solution, we don't have to wait for that. There are, in fact, 2 beta hydrogens available for E2 elimination here, and the hydroxide ion is going to want to approach either one of them. However, because of this hindered leaving group and the way the other groups are going to want to line up anti to it, this hydrogen is going to be not in an anti-periplanar orientation. That is, this hydrogen over here is not going to be accessible for anti. However, on the less substituted end, all of the groups are hydrogen, and so therefore it's going to be easy to get one of these groups to line up anti-periplanar to the leaving group. When that happens, we get an E2 elimination towards the less substituted position, something that violates Zaitsev's rule and is called a Hofmann elimination because it is Hofmann selectivity towards the less substituted alkene. And the major product of this reaction, in fact fairly cleanly, is 1-butene. So making the less substituted 1-butene, if that is your goal, Hofmann elimination is a good choice for your reaction. The leaving group here, of course, is the trimethylamine, the neutral amine.